Hello everyone, I'm Shankar. I'm just finished a PhD in a short postdoc at the University of Manchester, and I'll be moving to LMU Munich for a Humboldt Fellowship with Jochen Weller in October. And whoever organized the schedule, you did a great job because Harshada already made my life much easier by telling you a lot about modified gravity. But what I'll be talking to you about today is how we can best take advantage of all of the data that is going to be coming in our direction from all of these amazing large-scale structure surveys. So the plan is going to be, I'm going to basically give you some motivation as to why we need to modify gravity in the first place, which I'll breeze through really quickly. And then what are the main challenges in doing that? And then I'll talk to you about some of the work that I've done in collaboration with the group at Manchester on how you can predict cosmological observables from these n-body simulations of modified gravity and do that in a model-independent way. Compute weak lensing observables and compare fitting functions that predict these observables. And finally, some ongoing work. So these are only some of the issues with lambda CDM. So if your favorite issue isn't here, please don't shout at me. But obviously, we don't know what dark energy and dark matter are. But and I think this is something that people, or certainly not all people, talk about a lot. But general relativity, the validity of general relativity is assumed over a very large range of scales where it hasn't really been tested. And what I mean by that is that this is like a schematic or a cartoon where you have strength of gravity as a function of scale, and you have all of these really, really precise local tests of general relativity, things like the deflection of light from solar eclipses and so on. And you also have, obviously, cosmological perturbation theory on linear scales, but there's a whole host of scales in the middle where we don't really know how to test GR, and you shouldn't really be assuming that it works there when you haven't tested it. So that motivates you to try and modify gravity to explain the dark sector without the need to introduce these unknown components. And it's a mess, as you can see. This is giving you some idea as to what are the different ways you can modify GR in. And the point is that the model space is vast. So what do we want to do? We want to try and parameterize these theories using as few parameters as possible. And we want to do this in a way that we can include both linear as well as nonlinear scales. And that's particularly because planned experiments will generate ridiculous amounts of data on nonlinear scale. So what is the solution? The solution is what's called the Newtonian limit, which is this low velocity weak field limit, which you can derive for any or most modified gravity models. And it turns out that you can use this post-Riemann formalism, and this was shown by my collaborator Dan Thomas a while ago, that you can write down these two equations for the gravitational potentials. And this is a parameterization that is characterized by these two parameters, mu and eta, where this G times mu is this G effective thing that Harshada was talking about in the previous talk. And the really cool thing is that in this formalism, the density contrast, you don't need to assume that it's small. So this is essentially valid across all the cosmological scales in relevant and n-body simulation. The other really cool thing is that the matter geodesics, i.e. the dark matter trajectories, only depend on this equation and therefore only on this one parameter. So what that means is you can introduce a modified Poisson equation into an n-body simulation, and you can rescale Newton's gravitational constant, and you have an n-body simulation that of modified gravity. And what we've done is that we've binned this G effective into different bins in Redshift. And this is basically a step function that we've introduced. And these are the different bins. And the point here is not to try and mimic what is realistic or what hasn't been ruled out, but to gain some intuition as to what happens to the power spectrum. So here's some results from the simulations. What we've done here is that we've tuned the value of mu, that is this G effective over G, to be such that in all of our bins, when you extract the power spectrum at redshift 0, you have the same linear power spectrum and a completely different nonlinear power spectrum, depending on when and for how long mu is modified for. So this means that for the same linear power spectrum, you can get a whole host of nonlinear power spectra, which means that traditional methods like HaloFit will fail at predicting nonlinear matter power spectrum. And that's what this plot shows here. We compared a whole host of fitting functions in the literature to the matter power spectrum results from our simulations. And we found that this react formalism, which is a Halo model based approach, but the additional with the additional input of spherical collapse that allows them to calculate the nonlinear clustering. And the react formalism basically predicts our the power spectrum from our simulations to a much larger k, where this k fail is the first value of the wave number at which the power spectrum prediction disagrees with the power spectrum measurement from the simulation. So this pipeline has now been picked up by Euclid. So you have your cosmological parameters, and you feed that into a Boltzmann code at high redshift. And then you give it a small kick, and then feed that into your n-body code, measure the power spectrum. That gives you the matter power spectrum. And you also have this react formalism that allows you to do this quickly without the need of doing simulations every time. This is a nice pipeline. And now we can do cosmology with it. But what about that other parameter? There were two parameters that I showed you, mu and eta. And for that, you can compute the weak lensing observables, particularly the convergence power spectrum. And that is sensitive to both the matter power spectrum, mu, and eta over here. So nonlinear scales are important. The computing weak lensing observable shows you this explicitly. This is the linear prediction. This is lambda CDM with Euclid-like error bars for one of the tomography pins. And you can see the gain in information as you go to nonlinear scales. But the other cool thing is that you can break degeneracies. So for specific choices in parameters, you basically shift the power spectrum up in linear scales, on linear scales, but you affect the shape on nonlinear scales. And so you can break degeneracies between mu and eta. As you go from linear to nonlinear scales, you can see that some of these models diverge from each other. So this is nice. The other interesting thing that we saw in our simulation is that when you modify mu at different redshifts, as you modify it at later and later times, the transition, i.e. in the transition from matter domination to lambda domination, that is a smooth transition going from a dip in the power spectrum to a significant increase or an enhancement of the power spectrum when you increase mu. And this is compared to a lambda CDM simulation, but with the same linear growth. So this is important for what's going to come next. So I'm going to now talk to you a little bit about some ongoing work. So we found in our earlier work that if you modify the concentration mass relationship that React assumes, because React is based on the Halo model, and the Halo model assumes some density profile for the halos, and that comes from NFW, and in NFW you have this concentration mass. And that is a weak power law with mass. And basically what this means is halos that the more massive halos have lower concentrations, less massive halos have higher concentrations. So if you modify mu at early times, you produce more halos with higher concentrations. And so you expect the concentration mass relationship to be bumped up. But if you modify mu at late times, you expect it to go down relative to lambda CDM because you're producing more high mass halos. And that's what we saw. What I'm showing you here is the amplitude of the concentration mass relationship relative to lambda CDM. The data points are at the midpoint of the redshift bin at which we modify mu in the simulation. And basically the data points are calculated so that we maximize this K-fail parameter relative to the power spectrum. And we use React for this, of course. And the point is that as you go from high redshift modifications of mu to low redshift, you follow the expectation, as I said, which is you expect this amplitude to be smaller at late times because you produce more higher mass halos. But then lambda domination happens, and then you have that transition that I was talking to you about. You get a peak in the concentration mass relationship. So we saw that this shape of this fitting function for the concentration mass relationship persists for different bin sizes. D is just the linear growth factor associated to your bin, and mu is the value of G relative to lambda CDM. We found that this shape persists across different parameter values. And the point is, if you implement this fitting function into React, you get a much better fit to not just the matter power spectrum, but also the convergence power spectrum. So here's some future directions. We hope to implement this fitting function for the concentration into React and do a Rubin forecast. And we have people in desk like Agnes Ferte who are interested in doing this with us. You also have this cool method of cutting the power spectra at a specific K and propagating that out to the convergence power spectra. That's called K-cut cosmic shear. There's also ideas of speeding up these n-body simulations using hybrid methods, and then developing neural nets to make an emulator and then make the whole process faster. There's also splashback signatures that might be associated with the modified concentration. So lots of different ideas. I think this is really exciting, and I'm happy to take any questions.
Thank you, Shankar. So we can have a couple of questions.
Hi. Yeah, this is very interesting. So that React and your implementation, like a binned mu means like you can use each mu in each reference bin. You can take those as free parameters.
Yes, but I think there may be so you can definitely do that, and that's what we're hoping to do like Fisher forecasts and so on. Mm-hmm. But you want to be careful because we haven't tested it in a case where we've switched on multiple bins at the same time. Mm-hmm. So that's the idea behind trying to do this COLA stuff, where we try and make the simulations faster, and then switch multiple bins on and see what happens, and then validate React against that as well.
I see. Okay.
And then you can really go crazy with the MCMC and just use it as a completely free parameter.
I see.
But as of now, I mean, you can always do that, but we haven't validated that.
Yeah. Because I saw the paper at that time in just following the dark energy time evolution. It's not really correct thing to do. So this kind of direction is already necessary. This is my thought.
Thank you.
Is there any more questions? If not, then let's thank the speaker.